This is the screencast for section 4.5, example 5. We're going to use Newton's method to approximate the zeros of a function. Now, Newton's method, of course, does involve calculus. Basically, what Newton said is if we pick, so we have some function here that's got a root, a zero. We don't know what that is. But if we pick a random x value, and we use that x value to find a tangent line and find the zero of that tangent line, use the new x value to find the tangent line there, find the zero of that tangent line, because, you know, lines are a lot easier to find zeros of. Use that zero to find a new tangent line, etc. Eventually, that will lead us to our appropriate root. Now, that sounds like a big complicated process. It actually isn't. Remember, the equation of a tangent line is y minus y1, so we'll call that f of x sub n, the y coordinate here, equals the derivative at the slope at that value, and then times x minus x1, or in this case x sub n. So we're going to use this on the next page here. This formula is just a normal tangent line using fancy notation, and we're going to remember all these are finding zeros, so our y coordinate is actually 0 in this case. And now we can just rearrange some things. Just a little bit of algebra gets us this nice, neat formula to find a new x value. You're going to take your first x value and subtract f of x sub n divided by the derivative at x sub n. That's it. And we're going to follow this procedure over and over and over again. Now, there are two situations where Newton's method does fail. If we have the graph of the function, a piecewise function, negative square root of r minus x, and then square root of x minus r, so this function here, your approximations will actually bounce between x1 and x2, and this is just one example of when this may happen. So if you have a situation where your approximations are bouncing between two values, Newton's method will fail to converge there, and you won't be able to find the zero using Newton's method. Also, if you start too far away from the zero, so you got to have some mathematical educated guess as to where the zero is. If you start too far away, you're going to find the wrong zero. So if we started, here's the zero we're looking to find. If we start up here at this maximum, that tangent line is going to cross way over here by this zero, and we're going to end up approximating this zero, not this one over here. So you got to be careful. Again, make a mathematically educated guess as to where the zero is you're trying to find. So let's get down to it. How do you do this messiness? Well, remember, here's your formula. Your x value that you're going to start with is x sub n. And you're going to subtract the y value there divided by the derivative. That's it. And that will give you a new x sub n, so x sub n plus 1, a new one, every time you attempt this. And I can do this all in my calculator, which is really, really nice. So we're going to start out with 0.3 as x sub n. Now 0.3 is going to get stored as x. So now I'm going to tell my calculator, hey calculator, take x and subtract. Now I put in y1 the original function, and in y2 I put the derivative. So I don't have to type those formulas over and over and over again. I just tell my calculator, take the x value I just stored, x sub n, subtract y sub 1 divided by y sub 2, which will automatically calculate that x value, and store that as the new x value. So now my new x value is negative 0.322, etc. That's x sub n plus 1, my new one. Now I'm taking x sub n plus 1 and subtracting y1 divided by y2 of that new x value and storing it as my new x. So my new x, x sub n plus 2, is going to be this value. Now I'm taking that new x value and using Newton's method to approximate an even closer attempt at a zero, and I get x sub n plus 3. Then that new x value gets plugged in back again through Newton's method, and x sub n plus 4 is exactly the same value to every decimal place I can see, at least. Therefore, I can make a great estimated guess that the zero of this function is approximately negative 0.32218535546. Approximately. Now on your piece of paper, I would need to see what you put into y1, what you put into y2, and your new x values along with the formula at least once written down so that I can follow your process. You don't have to show me all of your work, but it has to be enough information where I would be able to reproduce your process and get the same series of numbers that you do. The now try problem number 15 asks us to do the same thing. Use Newton's method to estimate all real solutions of the equation. Make your answers accurate to 6 decimal places. Will do. All right, so I put in this case into y1, I put f of x, the original function. Into y2 then, I put its derivative, and I followed the same process. I first stored 0.8 as my technically x sub 1, and then I told my calculator, take that x value, subtract y1 over y2 of that x value, and then store that as my new x. So my new x now, x sub 2, is going to be 0.693150, you get it. And then x sub 2 is now going to go in and store as a new x value after Newton's method, an even closer approximation to our 0. And you can kind of see the 0 is a little bit less than 1, so this 0.68 is making sense to me. Pass that through Newton's method, and I get a new x value. Do it again. And eventually I get 2 values that are the same to every decimal place I can see. And then at least to 6 decimal places, which really I could have stopped after x sub 5. So the 0 in this situation is approximately to 6 decimal places, 0.682328. And I do prefer that you use the values, not n pluses, for your x's. So this over here should be x sub 1, x sub 2, 3, 4, and 5.